Check. All right, here. Seven.
Very short. So, first of all, I'm really honored to be giving a talk here in the graduate student seminar series. I've been waiting this talk for like a month now, but finally now I'm giving it. So, first of all, this guy, the Jeffrey Waller, he gave a talk on Riemann hypothesis. So, if you know about the Korean Mathematics Institute, it's the institute which was Salmon Millennium Problems in 2000. And previously it was at Harvard University, and recently I think it shifted to Oxford University. So if you go to the official YouTube channel of the Mathematics Institute, you will find a talk on Riemann hypothesis by this guy, Jeffrey Waller. And he's now a professor emeritus at University of Texas at Austin. Then comes this guy, Emmanuel Carnero. So he gave a talk in like 2001. And this was an official talk. And then this guy, Emmanuel Carnero, who is now a research scientist at ICTT, he gave a talk on the same subject, Riemann hypothesis, $1 million mystery at ICTT in 2017. And now me, I'm giving a talk today. So what's the link? So this is my master's thesis supervisor, and this is the advisor, PhD advisor of Emmanuel Carnero. That's continuing the identity. So I think everybody is seeing prime numbers. Okay, so prime number is a number which is greater than 1, and which can be factorized in only trivial ways, which means that the only number that it is divisible by are 1 and itself. So you might have also seen the fundamental theorem of arithmetic, which is a very striking result, which says that you can factorize every natural number as a product of primes in a unique way, which means that if you have two factorizations, they are same except up to rearrangement. So this was proved, I think, like 2,000 years ago. And then comes Euclid. Euclid enhanced our understanding of prime numbers by giving this remarkable result about the infinitude of primes. He said that there are infinitely many primes. So the list of primes is not, you cannot exhaust it. No matter how large natural number you choose, there will still be a prime number which will exceed that natural number. And my favorite prime number is 5061181. Guess why? Because it's the last 7 digits of my phone number. So you will later see, maybe we will see in this talk that only 1 out of 7-digit number, only 1 out of 16 7-digit numbers are prime numbers. So I guess I'm a little lucky here. So this is the Euclid's proof, which he gave in the 9th volume of his collection of books, which was titled Elements. So this book, this volume 9, is all about number theory. So he proves a number of results about prime numbers, in which he also proves this infinitude of primes. And this is the proposition 20 of his book. So if you see here, so he only sees numbers as length. His notion of numbers was just a length. So he gives this proof, and he only considers the 3 length, A, B, C. While the modern proof of infinitude of prime considers taking arbitrary number of primes and then showing that there must exist another prime. You can go and show, I think, so these 11 volumes on this work of Euclid was standard curriculum for mathematics up until, I guess, like 15th century. So he had a very impact on the progress of mathematics. This is the Euclid statue at the Oxford University. And now, so why are prime numbers interesting? Well, because they are kind of random, they are unpredictable. Unlike, let's say, a sequence of perfect squares, which is very predictable, or even numbers, primes are very unpredictable. They are, in a sense, random. So there are some problems which are very easy to state. You can maybe tell it to a high school or maybe elementary school students, but they're still open. Nobody has managed to solve them. So one of them is twin prime conjecture, which says that there are infinitely many pairs of primes which only differ by 2. A mathematical way of writing it is here, but just don't be scared by this. This is just kind of the same thing. This is still unproven. There has been major progress on this twin prime conjecture recently, like 2013, with the work of James Maynard and Zeta Yang. They proved that there are infinitely many pairs of conjective primes which differ by at most 70 million. And later Maynard reduced the 70 million number to 246. But we are still a long way from getting 246 down to 2. James Maynard, I think, won the Fields Medal in part for this result regarding this twin prime. So then there is gold box conjecture, which says that you can write every even number greater than 4 as a sum of 2 primes. For instance, you can write 4 as 2 plus 2, or 8 as 3 plus 5. It says that you can write every even number in this fashion. But nobody has managed to prove it as well. There has been partial results in this direction. For instance, it has been proved by, I think, Harold Helfgott, that you can write every even number, every odd number as sum of 3 primes. But this is still open. And then there's also this problem. I think this thing is one of the 4 Landau problems. It says that there are infinitely many primes of the form n squared plus 1. Okay. This is Christian Goldbach. And there is this book, Uncle Petros and Goldbach's Conjecture, which is very interesting to read. It is a story about a person who is a very accomplished mathematician. He goes to big universities, does a postdoctoral studies at Cambridge, and then he becomes a recluse and starts to prove a Goldbach conjecture. And then he proves something, and he gets excited, but doesn't publish it because he thinks that if I publish it, someone else will use my result to prove Goldbach conjecture. But finally, he proves a very exciting thing. Says he has to finally manage to prove something, not Goldbach conjecture, but very important result, and he shows it to another mathematician who then just disregards it and says that it has already been proven by an Australian mathematician. He becomes really disappointed and goes into depression. I think in mathematics. Okay, the story of Riemann hypothesis starts with the Basel problem. It states it was, I think, open problem for some time, like 50 years or 100 years. It asks you to solve to find the value of this series, which is the sum of the reciprocals of squares of natural numbers. So it was open. I don't know who actually proposed it, but Bernoulli's family tried to prove this problem, but they failed miserably. And then came the greatest of all, Leonard Euler. And I think this it is actually due to this result of Euler, due to which he became instantly famous among the mathematical community. So he proved that the value of this limit is pi squared over 6. And he used some result. So his proof was not very rigorous according to today's standard, but it was sort of like correct intuitively. You can make his argument work with that now. He actually proved find the value of the series for when you replace the exponent 2 by any even number. So he gave us this formula for this series of reciprocals of this powers of natural numbers when exponent is an even repeated. I think it's an open problem that Bernoulli's number. This is Leonard Euler, if you were wondering how we do it. Right. So next comes some major breakthrough in number theory. So Euler realized that you can write this series as this is called the P series. Usually, when you take the calculus courses, you can write it as a product of some quantity involving primes. And this is very easy to prove. Like at least you can see the proof of this and be satisfied. Okay, yeah, I think it works. It is very intuitive. But to make the arguments precise again, you need some analysis. So I'm not going to prove it, but this just states This actually follows from fundamental theorem of arithmetic. Okay. So Euler used this equivalence, this identity, to prove not only prove that the primes are infinite, but also prove that the reciprocals of the prime, the series of the reciprocal of the primes is also infinite. This gives us much more information than just saying that there are many primes. It says that primes are in some sense not very sparse, unlike like the sequence of perfect squares, which is very sparse. If you take the, they're very spread out. But primes are not very spread out. And even sometimes primes occur at with distance between two conjecture primes being 2, sometimes very large. Then we can find the prime. Okay. So next we move on to a major result in number 3, prime number theorem. So Gauss, he was investigating these. He was trying to figure out whether there is some kind of pattern in the prime. So what he did, he actually created these extensive tables of primes and tried to see whether there is some order or whether there is some pattern. So what he did, he actually calculated how many numbers, what is the ratio of prime numbers to, let's say, 100, and then to 1,000, and then to 10,000. What he noticed was that this ratio actually follows an arithmetic progression. And using this result, he conjectured this prime number theorem. So now it's called the prime number theorem because it's all has been proven, but Gauss couldn't prove it. Actually, it was Zaheer. So I'm going really fast and it's okay. That's what most people are able to follow. So Zaheer came along and
Prove this.
sorry,
Prove this.
I'm going to come to that later. So Zaheer came along, a Russian guy, and he proved he wasn't able to prove prime number theorem, and there's a reason for that I will tell you later. But he proved that phi of x does not exceed some constant multiple of x over log x, and the same from below. So he proved that the order of phi of x is x over log x. That because the conjecture is there actually gives more evidence about the prime number theorem. So people really believe that this might possibly be true. Because Legendre actually gave a similar, Legendre conjectured, I think, that phi of x is asymptotic to x over log x plus some constant. And so he was definitely wrong. And he thought that constant was something like 1 point some, 0 point something, maybe. But then Gauss conjectured this form, which was eventually proven to be true. Okay. So this filter just only means that if you take the ratio of the two quantities, it goes to 1. For instance, if you divide phi of x over log x, it will go to 1. This is what it's saying. Okay. So yeah.
A and B need not to be integer. Can be any real number. Positive.
No, they cannot be. They cannot be integers. At least A cannot be integer. B can be an integer. And A cannot be any real number. It has to be between 0 and 1.
0.
Okay. So Chebyshev used this result. I'm not sure, but I think you can use this result to prove Chebyshev's conjecture. Chebyshev's it was also goes by the name of Bertrand-Kirchhoff postulate, which says that between any number and its twice of its number, you can find a prime number. Using this result, with A greater than 0.5 and B less than 1.5, you can prove this. So he introduced some functions. So there is one function phi of x, which just counts and how many primes are there up to some quantity x. He introduced two new functions. These are like weighted functions. So he gives them the weight phi of log of x, and the phi of x counts the prime powers actually, but in fact higher prime powers are kind of negligible. But he gives the weight log, which is much easier, with a very smooth function log of x, which we can treat very easily. And he proved that if you can prove that phi of x is asymptotic to log of x, then this result is equivalent to proving the prime number theorem. And same goes for this theta of x. That if it's asymptotic to log x, if it is asymptotic to x, then you have essentially proven the prime number theorem. He also proves that if the limit of this ratio does exist, then it must be 1. Another way of saying this is that if the lim n is equal to lim slope on these two ratios, then prime number theorem follows. And the proof of this thing is not very difficult. It just follows from elementary things. So these are called Frederick Gall and Chagisha. So most of mathematicians that you will see live quite a long age. Not Frederick Gall and Chagisha, but you will see later Hadamard and Level on, they lived up more than 90 years. So that was great for mathematics because they contributed a lot of things. But there were some other people like Riemann who lived much, who died very younger. So prime number theorem was proved almost 100 years later when Gauss conjecture. The reason was that around mid-19th century, Bernard Riemann introduced a lot of complex analysis. He introduced all these tools and also quotient. They were introduced like quotient Riemann, quotient integral formula, quotient relativity theorem, which were eventually used in the proof of the prime number theorem. So it's not that Gauss was less of a genius than, let's say, Hadamard and Level, but it was just that the tools were not available. Mathematics were not right at that point. So this Hadamard was a French mathematician and Level was a Belgian mathematician, yes. So this is what I just said, that the tools for complex analysis were developed, and they were missing when Gauss, at the time of Gauss and Riemann. Riemann was actually involved in that. So Hardy actually believed that there cannot be a proof of prime number theorem that does not give this complex analysis. This was proved wrong by none other than Erdős and Atif in 1948 when they gave an elementary proof of the prime number theorem. So this elementary proof is although does not give this complex analysis, and anyone who knows a bit of calculus can easily follow their proof, but it's very opaque. Opaque in the sense that you don't see what's the motivation behind the thing, what's the motivation behind the result. So due to this result, Atif was awarded Peace Medal in 1953. I think he was just like 27, something around 27 or 33, quite young. So these are other ones, and this two. So definitely they were not that old when they proved prime number theorem. They were around the age of like 30s.
Something is wrong with the figure, right? Today's or the 90s.
Yeah, sorry, it should be 1966. You got earlier than you were born. So then comes to Riemann, and he introduced this Riemann Zeta function. He considered the Riemann Zeta function not only for real numbers but also for complex numbers. And he used the same Euler product formula that was introduced by Euler to study this Riemann Zeta function. So you see, on the one hand, you have just natural numbers, and on the other hand, you have prime numbers. So this is a very important identity due to the fact that here we can just use analytical technique on this series to study the property of prime. Using partial formation, this is a very simple result. I think if you know enough calculus, you can prove this. You can write zeta of s like this. So we have only defined zeta of s in this half plane when the real part of s is greater than 1. And you can write this zeta of s like in this form. If you look at this right hand side, you see that everything is analytic. Also this thing. This integral is also analytic in this half plane when real part of s is greater than 0. So this thing agrees with zeta of s for in its domain of definition. So we can extend zeta of s in this fashion for the real part greater than 0. So you can also see there is a simple pole at s is equal to 1, which is also very crucial in studying the properties of quantum. So then comes the gamma function, and we have extended the domain of definition of zeta from s real part of s greater than 1 to real part of s greater than 0. Now we want to extend it to the whole of complex number. And to do this, we require this gamma function. And maybe you know that gamma function satisfies this interesting functional equation. And using this functional equation, gamma function is initially defined for real part of s greater than 0. Using this functional equation, we can extend gamma of s to the whole of C complex plane, except it has simple poles at negative integers and also at 0, the G strategy. So another interesting fact about gamma is it does not vanish, which we'll show later to see to study the zeros of Riemann Zeta function. So if you take define this function psi of x as like this, you see that okay. So now we define the psi function like this. So I think I forgot to mention, but using the product formula for zeta, you can prove, you can see that it does not vanish in the half plane, real part of s greater than 1. Okay, so if you define psi of x like this, it also does not vanish because I've already remarked that gamma does not vanish, so it does not vanish. And now we can continue analytically continue this function psi to the whole of complex plane. Using this some properties of this Jacobi's theta function, you can extend this function psi of s to the whole of complex plane, except for two simple poles at s is equal to 0 and s is equal to 1. Some kind of question, I know, but I have to get to the actual content. So, okay. So I've already marked here that you can extend this using this. So this expression on the right hand side, this is analytic on the whole of complex plane. So similarly, we can extend this psi of s to the whole of complex plane with just two simple poles. Now, using this previous relation, we can write zeta of s like this. And this gives us the analytic continuation of zeta to the whole of complex plane. So we proved that, I think I forgot to mark here that psi of s also satisfies the functional equation, which I think I forgot to write here. Yeah. So this function psi of s is symmetric along the line s is equal to 1/2. And I already told that it does not vanish. So using these two things, you can see that zeta of s also does not vanish in the for real part of s greater than 1 and real part of s less than -1. Okay. So the only zeros of zeta that can arise are from this, either from this xi function or from the simple poles of or from the, yeah, so zeros can only arise due to the zeros of this psi function or due to the simple poles of this gamma function. But gamma only has poles at negative integers, and but the poles at s is equal to 0 kind of cancel out of this psi and this gamma. So zeta only has zeros at s over 2 is equal to negative integers, which means s is equal to a negative even integer. So in the half plane, s greater than real part of s greater than 1 and real part of s less than -1, zeta of s only has zeros at negative even integers. This is what I have written here. Okay. So Hardenberg and Poisson actually proved the prime number theorem by using the fact that zeta does not vanish on the line s is equal to 1 plus it. In fact, this fact is equivalent to the prime number theorem. You can show that. I've already told you that the zeros of the zeta of x correspond to the zeros of this function xi, which is analytic algorithm. So I've written it here. This is the functional equation of psi, and due to this functional equation, we can see that it's symmetric along the line half to the psi. Okay, so this zeta function is now defined in the whole of complex plane, and we know that there are no zeros to the right in the half plane, real part of greater than 1 and real part of less than 0. So we have this critical strip. So this strip between this vertical strip between the real part of S equals to 0 and real part of S equals to 1 is called the critical strip. And I've already told you that Artemis and Python proved the prime number theorem using the fact that real beta does not vanish on the vertical line where real part is equal to 1. Okay. So one natural question to ask here is how many zeros of beta are there from, let's say, imaginary part equal to 0 up to a certain height t. So Riemann in his paper actually gave a formula for this, which is the following. It grows something like t log t. So he was kind of vague about this formula, what actually means this. He didn't actually write what it means to be approximation here, but now we understand what does it mean. And so in particular, this formula also shows that there are infinitely many zeros of beta in the critical strip. G.H. Hardy and Littlewood, who were two of the greatest number theorists of the 20th century, proved that there are infinitely many zeros that lie on the critical line. So these are Hardy and Littlewood. Maybe you might have heard the story about the Hardy who recognized the genius of Riemann when he came and came to Cambridge and worked collaborated with Hardy. This is the Riemann's paper, and here he wrote this formula for the number of zeros up to a certain height t. It is t over 2 pi log t over 2 pi minus t over 2 pi. The writing is definitely kind of illegible, but at least the formula we can see. So now we finally get to the Riemann hypothesis. So we know that all the zeros of the Riemann zeta function, or at least the interesting zeros, lie in this critical strip. But Riemann conjectured that all the zeros lie on this critical line, which is S is equals to half plus IT, which lies exactly in the middle. So this is the famous Riemann hypothesis, which is still open. So it's like open for around 150 years, more than 150 years. It's also one of the Clay Millennium Prize problems. So the Clay Institute actually has proposed $1 million for each of these problems, each of these 7 problems. And only one out of these 7 problems have been solved so far, and it was Conjecture. In fact, it was solved just 3 years after they were proposed by a guy named, by a mathematician, Grigory Perelman, or a Russian mathematician. He was also a recluse icon Petros, and he in fact declined to accept this award. He also declined to accept the peace medal. Okay. So there are certain arithmetic equivalents to the Riemann hypothesis. One of this concerns the error term in the prime number theorem. So the Hadamard and Leverson proved that phi of x is asymptotic to x over log x, which is also asymptotic to this integral, which is called logarithmic integral of log. And but the error term, I think they proved that the error term was something like much greater than this. Now, if you can prove that the error term is this thing, x to the power half times log of x, then you have essentially proven the Riemann hypothesis. There is also another arithmetic equivalent which concerns this function phi of x introduced here, which says that if you can prove that the error term in this approximation of psi of x by x is at most x to the power half log square x, then you also deserve a $1 million prize. And then there is another one which relates to the Mobius function, which I will just skip for now due to the constraints of time. Okay, so Selberg proved that a positive proportion of the zeros of the Riemann zeta function lies on the critical line. So for instance, maybe out of 100, at least 1 lie on the critical line. This is not exactly what he proved, but you understand what he does. He says that at least a positive proportion of the zeros of Riemann zeta function lies on the critical line. This was a big result. Brian Conry, who is was, I think he's the president of the American Institute of Mathematics, something like that. He proved in 1989 that more than 40% of the zeros of Riemann zeta function lie on the critical line. So he actually sometimes remarked that he is entitled to 40% of the prize money associated with the Riemann hypothesis. So almost like 20 years later, Conjecture again proved that 41% of the zeros of Riemann zeta function lie on the critical line. It's just 1% after 20 years worth of effort. Okay, so this thing is interesting. Article Littlewood used to give Riemann hypothesis as a problem on the problem set of graduate students. In this definitely disguised form, it's not the theory completely. Just like our manufacturing who was here, Jacob's conjecture. Yeah. He was. On the time. So we have already seen that you can extend Riemann zeta function to the whole of complex plane. This is an analytic function which means it's nice, it has derivatives of all orders. And you can write this Riemann zeta function, this logarithmic derivative, which is defined as derivative of zeta of s divided by zeta of s as a Dirichlet series, which concerns fundamental function. And fundamental function is defined like this. It is only defined at prime powers, and at prime power it is prime power let's say t to the power m. It's defined as log of t. So it's kind of it's like a characteristic function of prime powers, except that it assigns weight to the prime. So using this duration, not using this, but using the standard tools of complex analysis, you can prove this simple result using just Cauchy's theorem or Cauchy-Ranity theorem. You can prove that this integral either equals 1, 1/2, or 0, depending on the values of x. So here it should be, I think, x less than equal to. So this will be important to kind of truncate this series. So right now this series is infinite, but using this thing, this formula, we can truncate this series and get something like this. So if we put in this logarithmic derivative inside the integral, we get a truncated series of the truncated Dirichlet series of one Mandel's function. Yeah. Okay. So using these sort of results, which actually this thing is called a LUMS formula, it gives you the truncated Dirichlet series if you give it to the whole series. And using these standard things in complex analysis and tools of complex analysis, you arrive at this explicit formula. So this is very interesting thing, because this is not an approximation or anything. It does not contain any error. It's the exact formula. It's an identity. So if we look at it, it concerns primes definitely, because the psi effect is related to prime powers. And then on the right-hand side, you have this non-trivial zeros of Riemann zeta function. Okay, I should have written that this row denotes the Riemann non-trivial zero of a Riemann zeta function. So to the right-hand side, we have information about the non-trivial zeros of the Riemann zeta function, and to the left we have function which concerns prime numbers. So this is how the prime numbers are related to the non-trivial zeros of the Riemann zeta function by this explicit formula, which was given by Riemann in his paper, but not in this form, I think, but was proved around 40 years later by von Mangels. So this is a hideous looking thing. I can show it. It's very looks very complicated, but it's not very complicated. You just play with this previous explicit formula. This explicit formula, and you get to this result. But right now, I'm going to skip. So I should say a word or two about this Montgomery theorem. So what you do is you use this explicit formula, which is written right here, and you just kind of rearrange the terms, and you end up with this thing. And then you also you replace S by you kind of reflect this formula along the critical line, and you get another formula, which is kind of a dual to this formula, and you are now you now have two formulas. And what you do is you subtract this third one from the second one, and on the left hand side you end up with this thing, and on the right hand side, if you subtract this from this, you end up with this thing. So if you see this, so this thing is equals to this thing, everything is fine except for we don't have exact information about these quantities which are appearing here. We can in fact write this their estimations which are given in the next slide. So this logarithmic derivative of beta, we can write it as minus log of absolute value of 2 plus 2 plus some bounded terms. So using these three estimates, we can rewrite this thing which appears here, this monstrous formula, and we end up with this thing. Sorry, no, I'm rushing. Okay. So we end up with this thing. So you might say, what's the use of this formula? But we will see later. Okay. So you also get this thing. So do you have any questions up to now? I think at this point I'm completely unanswered. Yeah.
At the end, I could have.
At the end, you can ask it right now if you want.
My question is, for example, if we manage to find commutative distribution function for the parameter, we just put a number and we can find all total numbers that how it can help us understand this theorem, or it can help us make our life better. I want to know the application.
When should I answer that question? Yeah. Okay, I think I'm going to find maybe I can answer it right now. So the prime number theorem, you're asking about the application. So they're using cryptography. Okay? So our banking data is secure due to large prime factorization of large numbers. So you can use results, some of these results, not exactly these ones, but related results, to get the algorithm for factorizing large numbers into prime factors. And if you can do that efficiently, if you can devise some algorithm which factorizes a number, gives you the prime factor, which does not have very high computational complexity or time complexity, then you can, I think, crack. It would be very bad for the banking banks because you can easily decrypt their information and get hold of millions of dollars, maybe something like that.
Okay.
You can become a billionaire probably.
There are theorems in mathematics that can only be proved assuming Riemann hypothesis.
Sorry?
There are theorems in mathematics that assume the Riemann hypothesis. So when you prove the Riemann hypothesis, you have many theorems that follow it.
Yeah.
Conjectures. Artif's primitive root conjecture.
Yeah.
How often is 2 a primitive root mod p? And only prove that it's assume Riemann at this point.
Yeah.
So with just one conjecture, Riemann hypothesis, with many theorems that follow on p.
Yeah, this is precisely why it's called Riemann hypothesis and not Riemann's conjecture, because it is used in the statement of many theorems. They just assume it to be true and then prove something else. This is exactly what the Montgomery theorem is going to do. It's just going to assume Riemann hypothesis and then give you some more information about the ZX. So far so good? I know at this point maybe some of these things are completely ununderstandable. Keep asking the question. So maybe I should just try to explain the original statement of the Riemann Montgomery theorem. Okay. So Montgomery used this explicit formula for Riemann from Neuberg, explicit formula to write at this formula. And this concerns this function f, and f is defined something like this. So this involves this omega function, which is defined like this, and so there is log appearance and a lot of things appearing. But if you look at it carefully, this only gives you information when alpha is bounded by 1. You see, this only gives you information when alpha is bounded by 1, and the Montgomery's conjecture will conjecture something when alpha is greater than 1. Okay. So I will just tell you what's the key ingredient in the proof of the Montgomery theorem. What you do is you arrive at this explicit formula, which is a lemma in the Montgomery's paper. And what you do is you take the root mean square of both these terms. There's a right hand side and the left hand side. And you kind of approximate this root mean square term, and what you end up with is this Montgomery's theorem. And this function f of alpha pops up naturally. So although you might see that it's very complicated looking, how can someone possibly come up with this formula, but it pops up naturally in the proof, in the course of the proof of this Montgomery's theorem. So most of the theorems in mathematics are like this way. So if you see the end theorem, the statement of the theorem, you are completely thrown away by it. How can someone come up with this? But actually, you kind of naturally just follow your nose and end up with that really. So this is exactly what I just said. That if you take the root mean square of the left-hand side, you get something like this. And using the simple algebraic manipulation, okay. So this root mean square is defined when you take the integral from 0 to t. And these gammas, these run over the ordinates of the non-trivial zeros of the Riemann Zeta function. But what you can do is you can extend this integral not only from the interval 0 to t, but to the whole of real line, and kind of restrict the ordinates of the non-trivial zeros of Riemann Zeta function to just those that lie in this vertical strip from 0 to t. And then you incur some errors, which is given by this big O term. So I hope most of the people are familiar with this big O notation. This just tells you that this error is not greater than this log 3t. This is not worse than this thing. Okay. So you just you do this algebraic manipulation, you square this thing, and you take the integral inside, and you end up with this thing. Yes. And it might be a good exercise for you to compute this thing. Using just the knowledge of calculus, I think you can prove this thing. In fact, last time when I was discussing this proof with my advisor, and he looked at this integral in instant, he works in Fourier analysis and harmonic analysis. So I was showing him this proof, and he looked at this integral in an instant, he said that I think it can be proved using Fourier analysis, I think. He went up to the board during this Zoom meeting and proved the result in just like 2 or 3 lines. When I tried to prove it, I like filled 3 to 4 pages, and still the answer was not correct. But he just went to the board and just using 2 or 3 lines, gave an elegant proof of this elegant result of this integral, and I was completely thrown away. Like I really thought that this guy is a genius. This guy is a real expert in this thing. So you get this thing. So if you see, that's what I was saying, that this function f of alpha pops up naturally. You end up with this thing, and you have this summation which involves this omega function, which is defined as like this, and you have this x to the power I iota gamma minus gamma prime. So previously we were just concerned with the sum, which is taken over the ordinates of just one ordinate of the Riemann Zeta, or non-trivial zeros of Riemann Zeta function. But now we have kind of a double summation. So we are now kind of exploring the relation between the zeros. And this function pops up, and then you can write this root mean square of the left hand side in this way. For some reasons, if you replace x is equal to 2 to the power alpha, this is just for convenience. You can just keep the x itself, but you will have more log terms that will be appearing to the right hand side. This is just for convenience, that if you substitute x is equal to 2 to the power alpha, you get this thing. And I'm not going to show you how to get this thing, but if you do some clever estimate, you end up with a formula for the root mean square of the right hand side like this. Okay. If you just equate these two things and do some simplification, you end up with the formula for f of alpha. But as I remarked earlier, this just holds for alpha, which is between -1 and 1. In fact, if you restrict it slightly away from the endpoint of the interval -1 to 1, then this thing converges, this thing holds uniformly. What I mean by this thing holds uniformly is that as t approaches to infinity, as t for each alpha, as t approaches to infinity, this thing will go to 0, this thing will go to 0 uniformly. So you might have seen previously that there was this f of alpha and f of alpha t here. So you might be wondering, here it was f of x t involved two arguments, but suddenly I just replaced it by just f of alpha. It was just that I'm considering it as like a family of functions corresponding to each alpha. And now I'm saying that it converges uniformly for each alpha. So this is a function. This f of alpha is a function of t. So this is the Montgomery's conjecture. Okay. So previously we just saw the information when alpha was restricted to the interval -1 to 1, but Montgomery using some heuristic argument ended up with this thing. And this thing gives you the information when alpha is beyond 1. But this is not very interesting conjecture. You might be wondering how does this relate to the Riemann hypothesis or the distribution of the zero of Riemann Zeta function. If you do some Fourier analysis, you can turn this information into something that looks like this. So I will do my talk with just making you understand this formula. So we have seen previously that if you take how the zeros of the Riemann Zeta function are distributed in this vertical strip. Here. So there are almost T over 2 pi times log of T over 2 pi zeros in the vertical strip from 0 to T. Okay. So what would be the average spacing between the two zeros? If we are assuming that they are distributed uniformly. You just divide this whole thing, you just divide T by this thing. Because there are this many zeros, you just divide the length of the interval by the number of zeros to get the average spacing. If you divide T by this thing, what would you get? 2 pi over log T, and this thing in the denominator is kind of irrelevant. And you get, so what does it say is that it counts the number of pairs of the ordinates of the Riemann, of the non-trivial zeros of the Riemann Zeta function, for which the spacing is beta times the average spacing between the two non-trivial zeros. So this 2 pi over log T is the average spacing between the two non-trivial zeros in this vertical line, so in this vertical strip from 0 to T. So it says that if you count and you assume that your spacing is less than beta times the average spacing, then it must look something like this. And there's a nice story behind how the connection of this thing with physics, which I think I will not be telling you right now because I'm tracking over time right now. And he ended up with this. So this is a conjecture with me that is still unproven, but there have been partial progress on it. And a student of Montgomery actually proved this conjecture for some certain clause of L function. So for instance, if the zeros of the Riemann Zeta function were uniformly bounded, what would we get? We should have just one here instead of 1 minus this sign of pi f x over pi f x. Instead of this weight function, we must have just one here. If we have one here, and we take 0 to beta, we will end up with beta times T over 2 pi log T. Which stays exactly the same. It is the same as this thing almost. It is exactly the information that is given by the Riemann formula. So I will just now end my talk with this famous quote of David Hilbert, who said that if I were to awaken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven? So this shows that the Riemann hypothesis, he also thought that the Riemann hypothesis is not very simple problem because of lots and lots of consequences in this important. So I just want to see my talk here, and just due to the constraints of time, I have to skip most of the details. I'm sorry for that.
How the three prime problems related to the
So in analytic number theory, there are two set of techniques. There are one that are called sieve methods, and then there is the theory of Riemann function. So the chain point conjecture comes in with the sieve methods, which definitely uses some results about the Riemann function, but I'm not sure how it does not relate very directly. And there are different domains. Yeah.
One more time.
I came to see some random matrices and perhaps some connection with physics. Could you say some words about that?
Yeah. Actually, I wanted to make the talk accessible to a larger audience because I'm very a lot of my other friends too, but I think it became completely inaccessible at times. So actually, I don't know myself much about random matrix theory because it's a new subject which developed around like in the mid 20th century, and I think physicists are more understand this subject because it was developed by Freeman and Dyson around the 20th century. In fact, there is a student who did this project on random matrix theory last year, and I said that I will consult you to understand more about the connection and understand pair correlation functions of the random matrix, eigenvalues of the random matrices. So I myself have not explored that area yet, but I hope.
My question is, if you look at all those theorems that you wrote it down, do you think it's okay to call it a theorem? Just look at the first statement of the theorem. It starts with assume part H, which has been open for 170 years. It's more like a philosophical question, right? Is it theorem?
That's like you
But it's assumed, I don't know. I think one can call it a theorem because if they teach you extra information, if you assume Riemann hypothesis, you prove this is true, maybe one day we hope that Riemann hypothesis will be proved and then it will be true.
Well, it's in a whole list of theorems of this nature. Sometimes they're called conjectures or something call them theorems.
Yeah, exactly. Like all those papers that are published that assume this Riemann hypothesis, they call them theorems. They don't call them conjectures.
Yeah. That would be the slope of physics, be careful.
and one of the very famous every first actor people used to the proof of the
Yeah.
and some very serious mathematicians also.
Yeah, even some very senior mathematicians sometimes claim proof of the Riemann hypothesis, which actually later turned out to be false. Recently, there was an attempt by Michael Atif, I guess.
Yeah, and I
Yeah.
Yeah, because I think the physicists are using the Riemann Zeta function and the theta function, particularly the string theories. So particularly they have some physical models, the physical integration of this particular theory. And I think Michael Atiyah's approach was completely physics. So it's Edward Witten and Michael Atiyah's approach in order to attack it. So all the arguments were non-mathematical. They were physical arguments to assert that. I think that's why I don't know Michael Atiyah product in that particular physics network and even I think they give that it's probably believe that we have to.
So there is one last comment that I want to make. Is that you might have seen this thing 1 plus 2 plus 3 plus 4 up till infinity is equal to minus 1 over 12. So now I will make you understand a little bit that compounding is class.
This is my
So this zeta function is defined like this. This is only valid when real part of s is greater than 1. So what about if we take s is equals to -1? But we know that Riemann zeta function has an analytic continuation to the whole of complex things. And we saw that zeta of s can be given by pi to the power s over 2, eta of s over gamma of s over 2. This psi of s is the analytic in the whole of complex things and can be said about this gamma function. So this series is not valid in this domain when real part of s is less than half, less than 1. So if we calculate zeta of -1, we get pi of 1 over 2, 1 gamma of 1 over 2. So if you calculate this, you can calculate this, and you will get -1 over 2. So this is the formula that works in this domain, in either half thing, when real part of s is less than 1. So using this formula, we get -1 over tau. And we relate it with this, that somehow this thing is equal to -1 over tau. If you replace s is equal to -1, you get summation of n. And it is equal to 1.
Shouldn't there be -1 by 2, gamma -1 by 2, instead of gamma 1 by 2, s is -1 by 2.
S is -1, yeah, you're right.
Same with the 5, the -1 by 2, these are -1. These are
Yes, yes. Yes, exactly. So that's how you get this quantity -1 over 12. And people try to relate it with this and say that the sum of all natural number 2 -1 over 12. Thank you.
Okay, I think, are there any other questions or comments? Okay, this is again, let us thank Atif for wonderful conversation. Well, you can